we will discuss how to solve a differential equation wherein we cannot evaluate using the integration, basic integration. So let us discuss first the first method wherein we will consider a differential equation of first order and first degree. So as we discussed in our introduction part that for the order, it should be first order. So for the degree is the exponent of the highest order. Now in this method, we will discuss the variable separable method. This is understood that for a certain differential equation, which is in the form of f of x plus n of y dy over dx is equal to 0. The idea is that m is a function of x alone, a continuous function of x alone, together with n is a continuous function of y alone. So then the idea is that if a given variables can be separated wherein we can combine the x with the dx and y with the dy. So this will be our solution for that. That we can collected all the terms for x with dx and the y terms for the dy. And then you can now just simply use the method of integration as we discussed in our previous lesson. So this method is the separation of variables or variable separable. Like in this example, we have, for our first equation is we have derivative of y with respect to x. So this is first order, first degree. And this is equal to x over y. So the idea is that just simply separate or combine the x with the dx and y with the dy. So then we can combine the y with the dy by cross it multiply. So the left side we can consider the y dy and then on the right side is x dx. And then when we evaluate this, they are both integrable. I mean the right side and the left side are both integrable. On the left side, this is y dy by means of power integral. So this is 1/2 y squared. And then on the right side is x dx. So this is also by power integral. So we have 1/2 x squared. And then upon integration, we have to introduce a constant c. So combining these two variables, we can consider that this is y squared minus x squared equal to c. Because for this one, we can also consider the c here as 1/2 c so that we can reduce the numerical value into or by 1/2. Another example here is we have dy with respect to dx or derivative of y with respect to x. And this is equal to x minus y over y cubes. And then obviously we can separate or we can combine the x variable with the dx and the y with the dy. So cross multiply again, we have on the left side is y cubed dy and then the right side is we have x minus 1 and then quantity dx. And then again, they are both now integrable, the left side and then the right side, and then the method is just simply by power integral. So on the left side, we have by power integral, this is 1/4 times y to the 4th. And on the right side, this is also by power integral, wherein we have to add 1 there. So we have x minus 1 raised to square over 2 or simply 1/2 of x minus 1 square and then upon integration plus c. So then all we have to do here is just simplify. Then we can simplify this by multiplying with the denominator of 4 here. So we have the y to the 4th and then this is 4 times 1/2 is 2. Then multiplied by the quantity x squared minus 2x plus 1. And then upon integration, plus c. Or sometimes you can just combine the two variables. You can transpose the x variables on the left side and this is equal to c. So it doesn't matter. Another example is we have the derivative of r with respect to s and this is equal to 4 over 9r. Again, you can obviously, we can separate the r or we can combine the r with the dr and then we can have this as dr over r and then the 4 over 9 ds. So the left side is now evaluated as dr over r and then on the right side as integral of ds. So for the dr over I, r, this is leading to loan. So we can say that this is ln of r. And then on the right side is just simply directly as s. Now, if we want to have a simplest form of solution, we can consider or we can introduce the loan or the constant c of integration as ln of c. So that we can combine these two. So we have here as we can combine the ln of r and then transpose the ln of c. So we can have ln of r minus ln of c by means of logarithmic property. We have r over c and then equal to 4 over 9s. Then we can reduce or we can remove the loan by just simply expressing both sides with the e or raise both sides with the e. So e raised to ln of r is r, and then on the right side is e raised to ln of c, e raised to 4 over 9 is just simply ce raised to 4 over 9. For the next example, we have how to find the particular solution. So if the given is variable separable, it is the same thing or similar with the previous lesson that all we have to do first is we have to look for the general solution and then we will just substitute the condition. So here we have xy dx plus e raised to negative x squared to be multiplied by y squared minus 1 dy equal to 0. And this is the given condition. At y0, y of 0 is equal to 1. So meaning to say when x is 0, y is equal to 1. So first is we have to find the solution of this differential equation. As you can see here, we can combine the x with the dx. So just simply divide by e raised to negative x squared here so that we can remove the x variable. So it becomes, and then divide by y on the first term. So we have here as x and then dx over e raised to negative x squared. And then on the second term, we have y squared minus 1 and then divide by y. So we have dy over y. Then, we can also express this as x e raised to x squared because expressing the denominator as numerator, so we have to change the sign of the exponent. And then we have divide by y here, so y squared divided by y is y, and then 1 over y is negative 1 over y dy. Then we can now evaluate. So we can evaluate the x e raised to x squared dx. This is simply integral of e to the u du. And then we have the y dy here as power integral, and of course the dy over y as leading to loan. So we might as well as we just combine the y variable here, so on the left side. And then on the right side we have the x variable. So we have to change the sign of it. Then this is now by power integral, we have 1 half y squared. And then for the dy over y is leading to loan, so minus ln of y. And then for this one is an integral of e to the u du. So we have to add 2 there together with correctional factor of 1 half. So we have negative 1 half e raised to x squared and then upon integration plus c. So this is the general solution. And then if we have to look for the particular solution, we have to substitute the condition that y of 0 is equal to 1. Meaning to say when x is 0, y is 1. So when we substitute here that y is 1, so this is now 1 half, and then we have ln of 1, and then for the e raised to 0 for the x squared, and then e raised to 0 is equal to 1, so we have negative 1 half on the right side, and then the ln of 1 is 0, so we only have 1 half on the left side. And then adding, transposing the negative 1 half, this is now 1 half plus 1 half, and this is equal to 1. Therefore, the value of the constant of integration here is 1 for the given condition that y of 0 is 1, or when x is 0, y is 1. Substituting the value of c here, so from our particular or general solution here when c is 1. So this is now plus 1 here, and then we can now simplify by multiplying with 1 half here. So we have y squared minus 2 ln of y and then equal to multiply by 1 half by 2. So this is negative 1 and this is times 2 for the 1. And we can also simplify this as y squared minus ln of y squared, because as for the logarithmic rule, we can express the coefficient as exponent. So this is also expressed as ln of y squared. And then plus e raised to x squared, and this is equal to 2. Another example is that finding the particular solution of the differential equation, we have y prime equal to 2 e raised to x equal to 0. This time, the given condition is that y of 0 is equal to 6, meaning when x is 0, y is 6. For the y prime, it can also be expressed as dy over dx. And then, obviously, this differential equation is a variable separable. Meaning, say we can combine the y with the dy and x with the dx. So, transpose the negative 2e to the x on the left side or on the right side, and then we can cross multiply or multiply by dx, so we can now have as y dy on the left side, and on the right side we have 2e to the x dx. And then it can now be evaluated as power integral, so we have 1 half y squared, and then on the right side this is integral of e to the u du. So integral of e to the x dx is just simply e to the x, and then upon integration plus c. So when we substitute the given condition, therefore we can look for the c here. So when x is 0, y is 6. So y is 6 squared, and then this is e raised to 0. E raised to 0 is 1. So this is simply 2, and then 6 raised to square is 36. Divided by 2 or times 1 half is 18. So transpose that 2, it becomes negative 2. Therefore, the value of c here is 16. Again, substituting to the given or to the derived general solution, when the value of c is 16, so this is now 1 half y squared equal to 2 e raised to x plus the constant c as 16. Then just simplify by multiplying by 2 to remove the coefficient, which is fractional form here. So we have y squared and then times 2. So we have 4e to the x, and then 16 times 2 is 32.